Okay, we're going to continue on lecturing on weak acids. I think is where we were at. So last time we talked about weak acid equilibrium. And remember that weak acids are weak electrolytes, which means, again, they do mainly stay together. So something like HF, which is hydrofluoric acid, and a weak acid will break apart into H plus and F minus. And remember, in solution, you do mainly have still the HF compound there still together. You have a little bit of H plus and F minus that is broken apart, which is why I still consider an acid, because it still is able to produce some H plus in solution. And because it is an equilibrium, we can write an equilibrium constant expression for it, just like normal, which would be H plus F minus divided by HF. And this is what is referred to as the Ka value, which is the weak acid dissociation constant. We solve these problems when we're looking to figure out what the pH of a weak acid solution is, really by doing an equilibrium problem. So we do an ice table. The real main difference is after we're done with the ice table and we solve for X, we're usually interested in this guy's concentration. And that would then allow us to really calculate the pH of the solution by just simply going into our pH equation. So you do need to do an ice table to figure out the equilibrium concentration of the H plus. You do it the exact same way, the X's. If you can make an assumption, you can do that. If you don't need to make an assumption, then you can solve it that way. Remember that if you do make the assumption, you want to make sure you check it so you don't have to go back and solve it some other way. But the nice thing is it really is pretty much the same deal as a regular equilibrium problem. Any questions on that? We also talked about the idea that obviously that is a super big hint that is a weak acid. So again, if you see any type of Ka value associated with any acid, it's proven to be a weak acid. And that should probably tell you should be doing some type of ice table to solve it. Remember, we did talk about some strong acids and some common strong acids you should be familiar with: hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydroiodic acid. So these are some common strong acids. For the most part, if it's not one of those guys, then you pretty much are good to go with the weak acid assumption. You'll probably be in the right if you do it that way. We also did talk last time that if you are given some type of strong acid or even a strong base, you do need to actually figure out what is the concentration of the H plus or OH minus, depending if it's acid or base. And then you can kind of go right into the pH equation or the pOH equation to get to the pH. You do not need to do an ice table with those because they will 100% break apart. And that is why strong acids do not have a Ka value, because they do not set up an equilibrium. Thus, they don't have, obviously, that reactant side available to them. Any questions on that? So I think we did an HF example at the very end, I think. Yes. And this just to remind you of, it is important to check your assumption. So if we really had kind of the same problem that we did previously there at the end, where we had this weak acid that dissociated into H plus and F minus, I feel like the Ka value we used was 6.4 times 10 to the minus 4, maybe. Yes. So initially here, this would be 0.05 molar, 0 change would be minus X plus X plus X, equilibrium 0.05 minus X, X and X. We would put this into our Ka expression, which will basically give us X squared divided by 0.05 minus X equals 6.4 times 10 to the minus 4. Now, if we assume that X is equal to 0, which we did on the previous problem, that would give us X squared over 0.05 equals 6.4 times 10 to the minus 4. Multiplying our 0.05 to the other side times 6.4 to the -4, and also doing a little square root action. I can find it on this calculator. Where did it go? There it is. That will give us a x value of 0.00567. And if we did check it, we would see that we're about, we divide it by this and times it by 100, we're about 11.3% in this case, which means this would be a very bad assumption, and we do need to go back and check it. So just a reminder that it won't always work. Even though the concentrations may look similar to you, one was 0.5 molar, I believe we did last time. This guy is 0.0 molar. So the concentration has a big effect as to whether or not the assumption will work. The one that is 0.5, right, is a higher concentration, which means the change is going to be a lot less than the 0.05, which is starting out very small. So any change is going to be relatively big. So you can think of it like a pizza, right? Get a new pizza, take one slice out, sounds good for dinner. Not a big deal, right? There's still plenty left. But if you're at the end of the box there where there's just 2 lonely pizzas left, right? And somebody takes out one slice, still only took out one slice, but a much bigger percentage of what you started with than it was with the whole one. So the concentration has a big effect in terms of, you know, whether or not that sort of assumption will work, and make sure you do check it so you don't get sad faces on your paper stats. All right. I want to do the turn that frown upside down speech. All right. So when we solve these, maybe you want to hear it. I don't know. So when we do solve these weak acid problems, like I said before, we really do work them the exact same way as a normal equilibrium problem, because frankly, they are an equilibrium problem. So that means you do need to do an ice table. The real main difference here is we are looking really a lot of times for the concentration of the H+. We will, in all cases in this class, ignore the autoionization of water. And what that means is, and most books do this, and we will do this, but some books don't on certain problems. The idea here is there is a certain concentration of H+ and OH- in the solution to begin with from water, right? Because water can attack itself. And in certain cases, the concentration of H+ in that solution from the water is actually higher than sort of your calculated H+ concentration. And they would say, well, then it's basically whatever water's H+ concentration is. So we're going to ignore that. So basically, we're going to assume that all the H+ that's in that solution is coming from like our acid. Nothing is coming from water. So we're going to ignore really water's contribution to the H+ and really the OH- concentration as well. In all the problems that we do here. So it makes it a little bit easier in certain cases. But I will say sometimes in books, they won't do that. So if you look at a problem or maybe look at a solution and they're like, well, hey, water has a much higher concentration, that's the reason for it. But most people will ignore sort of water's contribution and just assume that all the H+ is coming from either the acid or all the OH- is coming directly from the base, and nothing's really being contributed by the water. We again use the ice table to solve these sort of problems. And again, we could take our assumption if it works, but just make sure you check it. And there was some question, I think, last time, and just to reiterate, you don't have to do the assumption. You could, again, if you like rolling through, say, the quadratic formula and stuff like that, you can absolutely do it. As long as you do it correctly and carefully, it should come out the same. If everything works out the same. So you definitely don't have to do the assumption. It can just save you some time along the way. All right, so why don't you try one here? What is the pH of a 0.122 monoprotic acid, whose Ka value is 5.7 times 10 to the -4? Monoprotic means it gives away one hydrogen, right? And a generic formula for a monoprotic acid is HA. Yeah, so that's like the generic sort of monoprotic acid. By the way, a diprotic acid is something that gives away 2, and that's like the general formula for a diprotic acid. And a triprotic acid, if you need a kind of fake formula there, if you will, that's a generic formula for it. So we're looking at this guy in this problem, which is monoprotic. So give it a go, see what you come up with. Looking for what is the pH here. Okay, let's take a look, see how you're doing here. So first off, it's on monoprotic acids. So once again, like I said, if you ever sort of need some generic formulas to use and they don't really give you anybody, again, HA is generic for sort of monoprotic, H2A for diprotic, and H3A for a triprotic acid. We once again know in this case, because we are given a Ka value, that it definitely is a weak acid, which should automatically tell you I should do some isotable type work on this. So we're going to start with the reaction or the dissociation of our weak acid here, which is not that guy, but that doesn't really matter, I guess. Let's actually use the formula there. So we'll take our HA, it will dissociate into H plus and A minus. And once again, if you want to include water on the left-hand side, you would just have H3O plus, obviously on the right-hand side. Either way you want to do it, it's okay. Initially here, we have the concentration of our weak acid 0.122. This is going to be 0 and 0. Change here will be minus X plus X plus X, which means when we reach equilibrium, 0.122 minus X, X and X at this point. Any questions on the ice table? Like normal, we're going to put this into our expression, which in this case, the Ka expression, our products over our reactants. So it's going to be H plus A minus divided by HA. That will equal our 5.7 times 10 to the minus 4. Put it in our values there from our equilibrium line gives us X squared over 0.122 minus X is equal to 5.7 times 10 to the minus 4. We have a small value of Ka, so we could assume X is equal to 0. And when you do that, is it good or bad? If you didn't check, you should, because this is like 6.8%, which according to our 5% rule is bad. Yes. So you should not be using the assumption here because it's over 5%, which means we really do have to kind of go and solve it here using our quadratic formula. So we're going to multiply this to the other side. And if we do that, we will end up with X squared is equal to 6.954 times 10 to the minus 5 minus 5.7 times 10 to the minus 4x. Bringing everybody back to the left-hand side to combine our terms gives us our X squared plus 5.7 times 10 to the minus 4x minus 6.954 times 10 to the minus 5 equals 0 in this case. So this is going to go into our quadratic there of X is equal to minus B plus or minus the square root B squared minus 4AC divided by 2A. Putting our values in there, we will get, actually I'm going to flip the page, everybody good. So putting our values into the quadratic gives us minus 5.7 times 10 to the minus 4 plus or minus. If you do the inside part of the square root, you end up with 0.000278485. I clearly did one around there. And we will take a little square root action of that, and that will give us 0.016688 on the outside. That's all going to be divided by 2 times 1, which should be 2 in this case. Yeah. At this point, we're going to do obviously our two answers, our plus and our minus. And going the plus root there first will give us an X value of 0.00806. And doing our subtraction root will give us a negative 0.00863. Any question on that calculation there? Now, clearly, if we look at our ICE table on the previous page here, We are interested really in the H plus concentration, which does equal X at equilibrium. So clearly here we cannot use the negative value, right? Because that's going to give us a negative H plus concentration, which would not be good. That means by default, this one's going to be our winner, and that is going to equal the H plus concentration. And really at this point, since we do have the H plus concentration, that's all we need to calculate the pH. So we'll roll into our pH equation. pH is equal to minus the log 0.00806. Going to give us a pH of 2.09 in this case. Yeah. It is acidic, and so that does make sense. Now, if you did the assumption and didn't check yourself, you probably ended up at 2.08, which is fairly close. And the reason for that is it's only 6%, right? 6.8. So it's just a little bit above 5. So, you know, but for our purposes, it would be incorrect. So you got to do the quadratic formula here. And it won't always be that close in those situations, obviously, as well. Any questions on these steps? So hopefully you can see sort of a pattern. If it's equilibrium, do an ice table. Yes. I'll just say it, do an ice table. Yeah. You know, if you're not sure what to do, maybe try an ice table. It always amazes me. People get to the test and stuff or the final and they never do an ice table after going through this class where we do nothing but like ice tables. Yeah. So it's a good idea to keep that in mind. Any questions on this? But more importantly, hopefully you should see a pattern. It really is the same calculation. Here we're just kind of tweaking it at the end and put it into the pH formula. All right, so let's try another one here. What is the H plus concentration and what's also calculate the pH as well for this guy here? HCN 0.01 we're starting with a 6.2 to the minus 10 in terms of its Ka value. Okay, let's take a look and see. So once again, the Ka, big hint that we're dealing with a weak acid. So again, that should tell you should be doing an ice table. So we'll start with the acid dissociating. So we'll take our HCN. It will break apart into H plus and CN minus. Initially here, we got 0.01. We got 0 and 0. Change will be minus X plus X plus X, which means when we get to equilibrium, 0.01 minus X, X, and X. At this point here, we're going to again go into our Ka expression, which like normal will be our products over our reactants. So putting those in, we get X squared over 0.01 minus X is equal to 6.2 times 10 to the minus 10. That looks even smaller of a Ka value, so I am going to assume X is equal to 0 here. That will then give me a X squared divided by 0.010 equal to 6.2 times 10 to the minus 10. We're going to multiply that to the other side and also do a little square root on it. And if we do that there, 0.01 times 6.2 and a little square root for free here. Going to give us an X value here of, we'll call it 2.49 times 10 to a lot of zeros. 1, 2, 3, 4, 5, 6, minus 6, I think, if I counted right. We do want to check it. So once again here, we check it by dividing it by what we were going to subtract it from. So we're going to divide it by that and times it by 100%. So we'll divide it by 0.01 and times it by 100. And we're at like 0.02%. So this one is a good check in this case. So we can keep it here. And that would be our X value there. And we could go into our H plus concentration with And now into our pH equation, minus the log of 2.49 times 10 to the minus 6 minus the log 2.49 to the minus 6, like a 5.60 perhaps, yes. And that would still be acidic as it's less than 7, which is good. Any questions on any part of that there? So weak acid problems, basically same deal as everything else into that pH equation at the end. Good. Yeah. All right. So next thing we're going to talk about is actually was referred to as percent ionization of an acid. So percent ionization is sometimes referred to also as percent dissociation, basically how much it breaks apart. In the case of an acid, what that really means is what makes it an acid, right, is the ability to produce H plus or H3O plus in solution. So when we look at the percent ionization of an acid, we're looking at really how much H plus came off versus how much it started with. And that is the formula for percent ionization. It is the percentage, the concentration of the H plus that's in solution divided by the initial acid concentration times 100%. And if that looks familiar to you, that is basically how we check our assumption is what that is. That's basically how we check our assumption. We take our H plus concentration, which is usually our X value. We divide it by the initial concentration of the acid and we get a percentage. This is how we know like 5% ionization, it's okay or less, right? Anything more than that, again, it's going to be a significant change. It is dependent on whether it's a strong acid or weak acid. Obviously, a strong acid is 100% ionized, so it just completely breaks apart into solution, which, as we talked about, is why they are strong acids, because they produce a lot of H plus really quickly. A weak acid, it depends on the concentration. So what do we see in terms of percent ionization? When the concentration of the acid is low, the percent ionization is high, yes? And when the concentration of the acid is larger, the percent ionization is lower. Now it goes back to my pizza example. Again, if you had a whole pizza, take one piece out, not a big deal. If you have just 2 pieces left, take 1 piece out. It's more of what you started with, right? A bigger percentage of what you started with because you started with a much smaller percentage. So even a little bit of H plus that comes off in a smaller concentration will be a much bigger percentage change than in a larger concentration. So let's take a look at a problem here. We want to know, or we have a solution that is 8 molar formic acid, and it is 0.47% ionized. In this case, we actually want to calculate what the Ka value is. So let's think about how we can sort of attack this problem here. We definitely know that the formic acid is a stronger weak acid. Definitely a weak acid. Otherwise, we would not be solving for a Ka value. So that gives us a hint as to how we should kind of set it up. We probably want to set up the equation here with our acid dissociating. Bless you. We could also write our Ka expression for this, which would be, again, our product over our reactants here. And this equals what we're looking for, really, in this case. So we really can approach this kind of the same way as we do any other problem. We have a weak acid, we have a Ka we're looking for. Probably a nice table couldn't hurt to kind of put us in the right direction here. So initially what we know is we have 8 molar of our formic acid. We know we can usually start with zeros of these guys. The change here would be minus X, plus X, and plus X, which means when we get down to equilibrium, this would be 8 minus X, X, and X. Any questions on that so far? Now, normally what we would do at this point is take those guys and stick it into there and solve for X, but clearly in this case, we are looking for the Ka value. So we obviously use that. So the other piece of information that they gave us was that it is 0.47% ionized. So we could use our ionization formula there to help us out there. And what we just saw on the previous slide was the percent ionization is equal to the H plus concentration divided by the initial acid concentration times 100%. So we have this, which is 0.47. We obviously have this, and we have the initial concentration of our acid. So if we put that in there, we would have 0.47% is equal to the H plus concentration divided by their initial concentration of our acid, which was 8 molar times 100%, right? To solve for the H plus concentration, I'm going to multiply 8 to the other side and divide by 100, basically, or take 0.0047 of it. So I'm going to take 0.47 times it by 8 divided by 100. Going to give me 0.0. That's the wrong pen. Try that one. That is going to give me 0.0376 molar. Any questions on that so far? Why is solving for the H plus concentration a good thing here? Yeah, so if we look at our ice table, which is a good idea since we wrote one here, we look at our ice table, the H plus concentration at equilibrium is equal to X. So that really is the X value there. That would then be the X value here, and that would then be the X value here. So by using the percent ionization here, kind of like what we did with the equilibrium constant lab, where you kind of work backwards to calculate it, that's going to allow us actually to get numbers for everybody here. So we could actually put those in. So what we know here then is this is the H plus concentration. This also equals the HCO minus concentration, or the formate concentration. And the formic acid concentration at equilibrium would be 8 minus our X value. So if we do that, our formic acid concentration here at equilibrium would be 8 minus 0.0376. And that will give me 8 minus 0.0376. Gets me a 7.9624 molar. Now we actually have all the equilibrium concentrations that we need. And now we could actually put it into our expression here. So our Ka in this case would be 0.0376 times 0.0376 divided by 7.9624. And if we do all that there, 0.0376 times 0.0376 divided by, we will end up with a Ka value of 1.8 times 10 to the -4 in this case. Any questions on that? So using the percent ionization, that extra piece of information allowed us to figure out the H plus concentration at equilibrium. And then we could use that obviously to solve for everybody else. So this would be obviously a little bit more involved, sort of percent ionization type problem. A straightforward one would be you just calculate what the percent ionization of your acid. You could also do this for a base as well. The percent ionization of your base is basically how much OH minus comes off. So it works kind of the same way. Concentration of the OH minus divided by the concentration of the original base times 100. So it works for acids and bases. Any questions on percent ionization? Okay. All right, so then if there's no questions, the next thing we're going to talk about then in this chapter is Weak bases. So we obviously talked about weak acids. We could do really the same sort of calculation here for weak bases. Remember, as we talked about earlier, in all of the equations that you write, probably for the weak bases, it's a good idea to include the water so you can kind of visualize the Bronsted-Lowry definition happening, where it's going to accept the H plus there from the water. And that is really what's going to generate our OH minus in solution. We could write an equilibrium expression for this. This is ammonia, which is a weak base. We're going to take our products over our reactants. And once again, here we are not going to include the water like normal. And that would give us our NH4 plus and our OH minus divided by NH3. That is why in your lab, when you go to reach for ammonia, it says ammonium hydroxide, because in water, and it's an equilibrium with ammonium hydroxide and ammonia. And that is how we generate ammonia in that lab. So because it's an equilibrium constant, just like the Ka value, as the Kb value increases, the strength of the weak base will increase as well. And it's for the same reason as the weak acid. Larger the Kb value, more products. More products in this case means more hydroxide in the solution that's free. And that would make it a stronger weak base, if you will. Once again, it is obviously much weaker than any strong base like sodium hydroxide, potassium hydroxide. The sodium hydroxide, potassium hydroxide, those guys, they just need to go for a swim basically to produce the hydroxides. They 100% ionized. So these guys obviously are much weaker than that. We work these problems the exact same way, which means you do need to do an ice table. The only difference is at the end of the ice table, what concentration are you going to have? You're going to have the hydroxide concentration, which means in these type of problems, you usually got to take the POH route first and then to the pH. So remember that when you solve for X in this type of problem, it's not the H plus concentration, it is the OH minus concentration. And then that will get you your POH to your pH. That's why it's really important to know how to write these reactions, because people trying to McFake it, yes, the calculations, will just lay that thing into the pH equation and you will get the wrong answer. So make sure you understand what you're dealing with and you know how to write these equations. All right, so let's take a look at some weak bases. Obviously, there's a table in your book similar to this one where you might have to, for homework problems or something like that, look up a Kb problem. So let's give one a go here. We got Kb value for this guy here, 5.6 times 10 to the minus 4. We're starting with 0.15 molar. What is the pH of this base solution? I will do it as well, see if I remember. There we go. All right, let's take a look and see. So once again, a couple of things we're looking at here. Obviously, we have a Kb value, so that does tell us it's a weak base. So we do want to do an ice table. We want to write the equation. So we'll start with that. That's going to be a C2H5NH2. Again, a lot of people struggle with kind of what to react it with. Water would be good in the case of weak bases. Once again, the water is going to act as the acid. Our base is going to act as the base. It's going to accept the H plus, and that will give us C2H5NH3 plus, and a little bit of hydroxide, which again is what we would expect here, since this is a base. Any questions on the reaction there? At this point, we're going to roll like normal. So we're going to initially 0.15. We're going to 0 and 0. We're going to change minus X, plus X, plus X. And at equilibrium here, 0.15 minus X, X and X. Why am I not writing anything in the water column? Do we include water in the equilibrium expression? We don't. So really good idea not to put stuff there that you might want to use incorrectly later. So just leave it empty so you don't have the urge to kind of try to use the wrong thing. This is going to go into our Kb here, which once again would be our product. So in this case, it would be our C2H5NH3 plus. our OH minus divided by C2H5 NH2, and that equals 5.6 times 10 to the minus 4. Putting our guys in there, that's going to give us x squared divided by 0.15 minus x equals 5.6 times 10 to the minus 4. You could assume x is equal to 0. And of course, you checked it because you are professionals and you know that it was 6.1%, which based on our standards, no good. Yes. So we do want to solve it the favorite way, which is the quadratic. So we're going to move that to the other side. That is going to then give us x squared is equal to 8.4 times 10 to the minus 5 minus 5.6 times 10 to the minus 4x. Bringing everybody to the same side gives us x squared plus 5.6 times 10 to the minus 4x minus 8.4 times 10 to the minus 5 is equal to 0. Any questions so far on any part of that there? That gives us obviously our A, B, and C that we need to go into our quadratic there. So let's do that. I'm going to flip the page here and do that. Putting in our numbers into the quadratic there will give us minus 5.6 times 10 to the minus 4 plus or minus the square root. Once again, if you kind of clean up all the numbers inside the square root, you should get something like 0.000336314. Then if you take the square root of that, 0.01834, that's all going to be divided by 2 times a, which in this case is just 2 in this case. Going to give us our 2x values here. Going positive first will give us an x value of 0.00889. Taking the negative or subtraction root gives us a negative 0.00945. Any questions on that math there? So very much like the weak acid problem we just did, if we look back into our ICE table there, we are obviously interested in the hydroxide concentration, which equals X. So clearly we cannot use the negative number here again. So the negative number will not be good, which means this guy will then be our hydroxide concentration. That then could go into our POH. And that will give us a POH of 2.05. Remember again that if for some reason you thought this was the pH, it definitely should not make sense to you because that would then be an acidic pH and this should be a base. So again, in case you misthought about it there, that would not make sense. You could, but we're looking for the pH, so they want the value for the pH. So yeah, definitely at this point, you would know it should be basic. And by the way, you should know it should be basic to begin with because it was a KB and a weak base. So it should definitely be basic. Other questions? All right, at this point here, we got our pH plus our POH equals 14. That means that the pH here would be 14 minus our POH of 205. Going to give us 1195 there as our pH, which again does make sense since it is basic and this is a weak base. So we would expect it to be obviously above 7. Yeah. Question on any of those steps? I would say most people struggle with, I don't know how to write the reaction. So I'm not sure if it's OH minus or H plus or what's going on the other side. And the second thing most people struggle with on this one is they think it's the pH at the end of the ICE table there, so not the POH. So those are two very common pitfalls that people kind of fall into. Yeah. Any questions on any of those steps there? So weak acid problems, Kas, weak base, Kbs. Any questions on that? So when we look at the Ka value or the Kb value, they do come from obviously the dissociation of a weak acid in the case of a Ka, dissociation of a weak base in the case of a Kb. Now, when you look at certain problems that you'll come across in this chapter and other places, you oftentimes will maybe be given the wrong K value. What I mean by that is they may give you the Ka value, but you really need the Kb value to do the calculation, or you may be given the Kb value when you really need the Ka value. First off, let's start off with very basics here. How do I know I should use a Ka value versus a Kb value? Any ideas? I should use a Ka value when I look at my equation. I see what on the product side? I see this guy. I see H plus or H3O plus. You should be laying up a Ka. Again, why it's really important to be able to write these equations so that you can see what's on that side, and it helps you with the math part of it. If you are using a Kb value, you best be seeing a OH minus there on the right-hand side of the equation. Otherwise, you probably are doing it wrong. So again, I can't emphasize enough how important it is to be able to write these things. It helps you with the math. It helps you kind of go in the right direction there if you don't overlook all these things that can be very helpful. So what do you do if you come across a situation where you're given the Ka value, but you really need the Kb or vice versa? There is a relationship between the Ka and the Kb. If you add both of those reactions together, the weak acid with the weak base, we make our good friend water, which is also in equilibrium. And that is what we saw earlier, which is Kw. And that is the 1 times 10 to the minus 14. So if you ever need to kind of swap out between a Ka and a Kb value, the Ka times the Kb equals Kw, which is that same number that we used previously, 1 times 10 to the minus 14. By the way, why are we multiplying these two things together, the two K values? That is what we talked about in the previous chapter. When you add two reactions together, you multiply the K values. So that is why we're multiplying the Ka times the Kb value. So that is a very helpful sort of thing, especially when we talk about salts, which is historically, they give you the wrong K value in the problem. So they give you the wrong one to use, and you do have to use this relationship. Obviously, it's the same calculation regardless of which way you need to flip it. It is 1 times 10 to the minus 14 divided by either Ka value or the Kb value. Any questions on that? So that definitely is something to keep in mind, and you will definitely use that along the way in a variety of sort of problems that we'll come across. So let's talk a little bit about the strengths of acids. And there's really two types of acids. There are acids that do not contain oxygen. And when we look at acids that do not contain oxygen, really the main thing that we look at in terms of acid strength is actually bond enthalpy. And it's not electronegativity like you might think. Electronegativity, right, is the ability of an atom to bring electrons towards itself, right? And in this case, if you are comparing acids that do not contain oxygen, we actually look at what is known as the bond enthalpy, which you might have talked about when you did bonding. But there is a certain amount of energy required to break bonds, single bonds, double bonds, triple bonds. If you took being your members, like the one we had to do all the accounting, we broke like 3 single bonds, made 2 double bonds. You add up all the bonds you broke energy, all the bonds you made, subtract them or add them together, and depending on how you do the sign, and you'll get that. So when we look at the bond energy here for group 7, which is pretty much where all these acids kind of come from, what we see is actually HF has the highest bond energy, which means it is harder or easier to break this bond. is harder. And what makes something an acid is that bond needs to be broken. So because it takes a lot more energy to break that bond, it's going to make HF a weaker acid as compared, bless you, to the HI, which has a much lower bond energy. And because it has a lower bond energy, it means it's not as hard to break that, which means it will come off a lot easier and thus be a stronger acid. So when we look at acid strength in group 7, it actually increases as you go down the group. That's why we added to our list HI and HBr as strong acids, along with HCl, and HF is a weak acid because it takes the most energy to sort of break it apart. Any question on that there? Now, when we deal with acids that do contain oxygen, they are sometimes referred to as oxyacids. And when we look at oxyacids, because they do contain oxygen, we really look at one of two things depending on the situation. We look at sometimes electronegativity, and a reminder, electronegativity, right, increases as you go this way on the periodic table, decreases as you go this way. Most electronegative atom is fluorine, right? It's the most electronegative atom that you could have. What is the bond in a oxyacid that is the acid part of it? It's that OH bond. Yeah, so it is that OH bond in an oxyacid. That is the H that comes off. OH bond is polar to begin with, right? Which means it has unequal sharing of electrons. By the way, electrons would be heading towards which one here? Be heading towards the oxygen, right? Which means this bond is sort of weak to begin with. So depending on what we got going on in terms of electronegativity or the oxidation state of the central atom can determine how strong or how weak an acid is. So let's talk about which one we should look at in which situation. Let's say we have these two acids. And if we have a different central atom on these two acids, and they're from the same group and have the same oxidation number. By the way, if we want to assign oxidation numbers, good place to start is oxygen has an oxidation number of -2. Yes, -2, -2 plus 1. That's a -6 and a +1, which means to balance it out to 0. In this case, since it has no charge, the chlorine has an oxidation state of +5. A reminder that oxidation states are not the same thing as ionic charges. So in an oxidation state, because there's sharing of electrons, they take on perhaps a different sort of charge than you normally associate. In this case, the chlorine is taking on a +5 charge from sharing electrons with all those electronegative oxygens that are next to it. Same thing here, if we roll through on the guy over here, that's -2, -2, -2 in terms of the oxidation state. Hydrogen is +1, which means again here, the bromine is also +5. So clearly in this case, we cannot look at the oxidation number as a determining factor in terms of acid strength. So in this case, when you have the same oxidation number on the central atom and an oxyacid, you look at electronegativity, and acid strength increases with electronegativity. Between chlorine and bromine, which one is more electronegative? It is the chlorine. It's further up in the group, right? So going up is more electronegative. So what does that mean? It means, frankly, you have this bond that is the electrons heading this way towards the oxygen. And now you have this guy that's more electronegative, which is going to pull the electrons even further in. All that's going to do is weaken and weaken that bond and allow the H plus to basically pop off. So really all those electrons are going to be drawn in towards the center of that polar bond, weakening it and allowing that H plus to come off, which would make it a stronger acid than the HBrO3 here. So in this case, it would be the HClO3, which is chloric acid, would be stronger than bromic acid in this case. Any questions on that? Now, the other situation you could have is kind of the opposite situation. You basically have somebody where you have the same electronegativity, but different oxidation numbers. And in a case where you have an oxyacid with basically the same element in the center, in this case, they all have chlorine in the center, which means they all share the same electronegativity. What we look at is oxidation numbers. So once again, to assign oxidation numbers, start with oxygen as -2. So that is -2 for this guy. Hydrogen is +1. That is a -1, which means the chlorine in this case is +1 in terms of its oxidation number. Over here, the oxygen is -2 here, -2 here, hydrogen +1. That's -4, and +1 is -3. To get it to 0, the chlorine in this case would be +3. Once again, here, this is the one we just did on the other page, -2, -2, and -2, and +1. Chlorine in this case will take on a +5 oxidation state. And lastly, here, perchloric acid, -2, -2, -2, and -2, +1. So that's a -8, and +1 is a -7, which means the chlorine here would take on a +7 charge. So the strongest acid here should be which one? Should be the perchloric acid. Again, same idea, same reasoning. In this case, you have the polar bond here where electrons are heading towards the oxygen. Now you have this big +7 charge there, which is going to bring the electrons in even more. And that again is going to weaken that bond a lot easier and allow the H plus to come off a lot easier than the +1 pull that you would feel for this guy. So in terms of the acid strength, this guy would be your strongest, followed by this one, and the weakest acid there would be hypofluorous acid at a +1 oxidation state. Any questions on that? Okay. All right, good place. We're going to lay it up there, I think, for today.